Hi, my name is Chris Sanders, and I am here to lead the Creating and Using Synthetic Data for Computer Vision Applications presentation that the Rendered AI and NVIDIA team delivered for CVPR 2022. Today we're basically going to do a recap of the presentation that we gave live. There were some audio-visual recording problems, and we're happy to do a condensed version for an at-home audience. We're going to cover an introduction to physics-based synthetic data, discuss running an experiment with synthetic data in NVIDIA Tau. We're going to talk about developing a synthetic data channel, which is basically a synthetic data application inside Rendered AI. And then we'll discuss how to extend synthetic data workflows. The presenters today are myself, Chris Andrews, Katya from NVIDIA, who's our guest presenter, Dan, our lead solution engineer at Rendered, Sam, who is a release engineer here at Rendered, and then Matt, a senior software developer here at Rendered. I am the CEO and head of product for Rendered AI. I have a couple decades experience in product development, product management, and leading startup groups both inside larger companies and then at small companies. My focus historically has been in 3D, geospatial, and a variety of domains related to geospatial. Katya joins us from NVIDIA. She is a senior data scientist. She has a PhD in computer science and a master's in media informatics. She has specialized in solving computer vision and video analytics problems using AI. And these days she's traveling the world basically presenting on NVIDIA Tau and other NVIDIA data science tools, and she's helping customers solve problems every day. Dan is our lead solutions engineer, and he has about 10 years experience in the geospatial industry. He's a subject matter for us in remote sensing, 3D, and then feature extraction from 3D data. Matt joined us as a senior software engineer. Matt has several years of experience overseeing AI-based product applications, and he's got a bunch of experience in machine learning development and a background in physics. And Sam is our release engineer. She has 6 years of full stack experience as a software engineer. She's got a BS in computer science, and she's studying for her MS right now. The key points that we would like you to take away from today's class include the rationale for using synthetic data, definition of physics-based synthetic data, which is what we focus on, roles and skills for staff who are going to be developing synthetic data, typical workflows for success, benefits of using a platform for data generation, and then examples of actual synthetic data applications. Rendered AI offers a platform as a service for synthetic data that enables data scientists to overcome the costs and challenges of acquiring and using real data for training machine learning and artificial intelligence. We're headquartered in Bellevue, Washington, with all remote operations. We have a subscription-based hosted platform that was released late last year, and we focus on computer vision use cases, including generating X-ray images, satellite data, life sciences, and much, much more. For the purposes of the live class, we asked folks to go to Rendered AI, click the Get Started button, and then sign in to register for an account using the content code shown here. That should still work after the class. You also should sign up for an account with NVIDIA NGC because there will be some tools used through NGC in parts of the demos. One note was that you must have a Google account to use Vertex AI, which is part of one of the demos. Okay. As I'm sure most of you know, data access is one of the fundamental limiters of AI. We see that rare events and edge cases can be extremely hard to find in real sensor data. There are often data labeling problems. It's not only expensive, but sometimes just hard or even impossible for humans to identify and manually label features or classify areas within imagery. And then some data is just simply not human readable. For example, radar images, IR, and then other non-visible light spectra can be really difficult for humans to label. Lack of data can be a barrier to innovation. In many cases, we're finding customers who want to experiment with data sets for future sensors or scenarios that simply don't yet exist, so for which they cannot yet collect data. And then, of course, in broader parts of the industry, we're seeing a lot of information about restricted or high-risk data. Gartner calls it radioactive data. That is really difficult to use for AI training without risk. And that can include security, medical data, PII-based data sets, things like payroll or legal information, and even things such as faces, and in some cases even houses or other identifying marks or possessions of people. Synthetic data has the potential to solve the AI data problem. Synthetic data is essentially engineered data that an AI interprets as if it is real data. And what we're seeing in the industry is that Gartner and many other publication groups believe that synthetic data is going to be used for a significant amount of the data used to train AI, both in the next couple of years and even increasing in the long run. And as Forbes said in their recent article, the net effect of the rise of synthetic data will be to empower a whole new generation of AI upstarts and unleash a wave of AI innovation. As I said on the last slide, we see that data as a critical limiting factor, even for just innovation around how to use AI in the future. We are seeing lots of news about synthetic data. There's increasing activity around investment and acquisitions, executive thought leadership, especially from larger companies such as Amazon and NVIDIA, Meta, and many others. There are more and more proof points coming out every year, and then of course we're seeing more technology developed around synthetic data creation. When we talk about synthetic data at Rendered, we are specifically talking about physics-based data that emulates real sensor captured data from the field. For example, this could be passively captured data such as video or camera imagery, hyperspectral imagery from a satellite sensor, and many other passive capture domains. It can also include more active sensors such as radar. We actually have our own physics-based SAR simulator, for example. Rendered AI can technically be used to generate any kind of synthetic data, but our initial focus has been on physics-based synthetic data generation for CV workflows. Typical output from the Rendered AI platform includes 2D imagery, 3D models, additional 2D and 3D content, metadata, and annotation that is used to train AI models. If we look at today's AI workflow, what we often see is that customers are focused on basically scraping together the data that they can find or buy to train algorithms, test them, and then basically get what they get. There's a variety of manipulation that can go on with real data sets to try to improve AI training, but at the end of the day, you're limited by what's in your data. This can be expensive. It can have unpredictable data acquisition costs. It can be difficult to train on inconsistent data. When you test and validate using real data sets, you often have to split up the amount of real data that you have, which even further reduces the utility of the data. And then fundamentally, your results are limited to what you can achieve with real data sets. We see that tomorrow's AI workflow incorporates synthetic data in a much more iterative workflow that basically starts out by enabling a user to create data, train algorithms on it, test the algorithms, and then compare data sets to see if they then need to go modify their data creation pattern and then create more data. One of the ways that we often start out working with customers is to ask, what is the ideal data set that you think you need to start off this process? This allows the customer to start out from a position where they're going to be able to generate very inexpensive, unlimited data sets that are 100% accurately labeled. Real data sets can be used for comparison and post-processing, and then data can be designed for edge or impossible cases and for removing bias. Many customers come to us and conceptually believe that synthetic data generation works by taking a simulator, building data sets, and then training AI models, and then going away and being very happy with the result. Unfortunately, what we've seen over and over is that this simply doesn't work. what we find is that individual data sets don't solve the entire problem that a customer is looking for. Often the initial data sets that are developed don't actually work for what the customer believes that they're trying to, for the customer's training problem. Synthetic data capabilities, as we've observed, must be continuously improved and extended, and successful users need an iterative workflow. For us then, this tends to break down into three different components. We see a new role in the market called the synthetic data engineer, basically driving world building and simulation capabilities for the customer. We then see that synthetic data applications built by the synthetic data engineer will be deployed to manage compute, which is where platforms like Render come in. And then we see data scientists being able to easily generate dataset jobs, retrieve datasets, conduct quality assessment, and then train AI models. And from there, if they need more changes to the simulation tools that have been built, they can then work with synthetic data engineers to drive more variability or more post-processing effects or other things into the world building and simulation that goes on to create synthetic data. Through this iterative process is how we see customers arriving at improved and explainable outcomes that actually solve the problems that they're trying to address. We believe a job of the future is going to be something called a synthetic data engineer. As Gartner is saying, if a ton of data in the future used to train AI, in fact, they believe most data in the future used to train AI will be synthetic, there must be, therefore, a job role, a job function for someone who will be engineering that data. Synthetic data engineers are likely to be designing and engineering data sets to achieve specific business-focused AI outcomes. They will often be software development oriented. They'll be used to things like iterating in development activities by using tools like Python. They may be familiar with certain data science skills and toolkits. They may be familiar with things like 3D or game engines. These synthetic data engineers may also have specific vertical industry expertise, for example, in healthcare or other life sciences or remote sensing or many other vertical domains that use computer vision. And then they will often be expert in specific data types and technologies. So this could be specific types of sensors or renderers or modeling or other simulation technologies. The skills that we tend to run into being needed by customers to actually build synthetic data applications include things like having sensor domain expertise. So for example, we're seeing more demand for things like hyperspectral imaging, synthetic aperture radar, and even just classic RGB imagery in the remote sensing domain. Some folks will definitely need to have AI training data wrangling skills. They'll need to be able to understand things like how to compare data sets and then how to even mix and match synthetic data sets with real data sets. All focused on a specific domain problem. Of course, customers need familiarity with data science concepts and techniques. And then we see technical skills that are required to build synthetic data, including things like Python programming, familiarity with 3D, and then a variety of other possible vertical domain tools and toolkits, such as, for example, a lot of demand we're seeing around the geospatial industry. Synthetic data generation tends to be an empirical process. We often work with customers to back them up from a place where they are today, where they're scraping together data and they're basically making do, and we have to ask them to more clearly identify the problem they're trying to address. From there, we often work with customers to help them describe the ideal data set that they think is needed for training an AI or solving a problem. We then help them generate data using the rendered platform, or they may even build out the synthetic data applications to generate data themselves using our platform. Then they see if they can achieve any training accuracy at all. From there, they often refine data generation, and then once they've achieved a certain level of training, that's kind of their minimum expectation, then they apply other techniques to see if they can improve training even beyond where they got with their initial data generation. We find that the synthetic data generation process tends to have a variety of different distinct components. There is one step where a customer may be required to characterize the scenarios that they need in their synthetic data. This typically ends up being a requirement to understand what data types are being output, what kinds of variability are going to be required in the data sets, and then some focus on which specific problems are being addressed or tested. For example, remote sensing, you may be in some cases just trying to count objects. In other cases, you may be trying to count objects that are being obscured by cloud cover or by other in-scene objects or assets. From there, customers often then need to pull together all the components that will make up the world that they're simulating. We also end up working with customers who need to describe the sensors that they're modeling and the actual simulation effects that are required to emulate the actual operation of those sensors in the real world. Annotation and mask calculation can have specific requirements depending upon the types of data sets and problems that customers are trying to solve and need. We may help customers employ things like domain adaptation for post-processing to make synthetic data sets appear more like real data sets. And then there is a phase of job execution and dataset compilation. For a customer to basically do this on their own, they will be essentially building their own cloud infrastructure and content management systems to be able to run lots of jobs and then manage all the data sets. And then finally, Rendered provides and other vendors provide some capabilities to actually characterize and compare data sets. We typically talk about some distinct phases of effort during the synthetic data, what we call channel development activity. A channel for us is a focused synthetic data application that is designed to output specific types of computer vision content plus annotation and other metadata that will be used to train AI around a certain domain. That could be a simulation real-world scenario domain, or it could be specific sensor modalities or domains. And so channel development typically is conducted by the synthetic data engineer that we talk about. Sometimes this may be a database engineer. And what they'll be doing is aggregating and creating scene content, modeling digital sensors, and then creating the configurable channel that will then be deployed to the rendered platform, where computer vision engineers and data scientists and even automated workflows can basically take those channels, create and configure drafts that will drive the specific execution of jobs on the channels, run jobs, get data sets, and then take the data sets outside rendered and train and evaluate AI. Channels for us often become open source examples for customers to build upon. Our basic example channel that we have is Blender based, and it basically is a box of toys that operate as the objects of interest that are then combined with a simple RGB camera sensor and some very basic configuration about how the sensor and lighting work in that environment. And then user can use this to generate images, data sets. From there, we also provide, outside the channel, we provide CycleGAN microservices for domain adaptation. We provide custom annotation services and a variety of other things within Rendered. Underneath it all, Rendered provides job management, user management, and role management, archive and search, and a variety of other capabilities in Rendered AI Cloud, so that customers can basically focus on building and configuring the channels that they need for their data sets without having to worry about all of the management activity that goes on around running jobs in the cloud. Our typical example channel focuses on using Blender as a renderer. We also offer an ArcGIS channel that allows customers to retrieve 2D raster backgrounds for simulated remote sensing information. We are working on an Omniverse channel so that we can use NVIDIA Omniverse and extensions. This will include a variety of pre-installed dependencies specifically for Omniverse, but otherwise will function identically as the Blender channels function. And in the future, we'll be adding a variety of other channels focused on tools such as DeerSig and even other renderers and game engines that are out there in the community today. Ultimately, the point of providing a platform is so that our customers don't have to rebuild everything for every AI application. And what we are doing is building out this capability to capture sensors and sensor platforms for specific vertical applications in a modular architecture that can be deployed to the cloud, and that includes content pipelines, sensor models, analytics tools, and integrations to popular AI toolkits such as SageMaker and to NVIDIA Tau. The ultimate goal of providing a platform is to reduce the total cost of ownership to our customers to enable them to access synthetic data as an enterprise capability. Along with the rendered platform, we focus on providing tools that enable the complex workflow that it takes to make synthetic data generation successful. Typically, we break this up into channel building, data creation, post-processing, and then integrating into other pipelines. In this case, with the National Geospatial Intelligence Agency and Orbital Insight, we conducted a study where we helped the customer search for cranes and crane trucks as economic indicators in satellite imagery. These objects are relatively rare compared to other features in overhead imagery, and labeling them can be really difficult for humans. The Orbital Insight case study was able to demonstrate that we were able to increase the average precision of model training by combining real and synthetic data, and it also demonstrated that overall we were able to reduce the total amount of data required to train AI. There are many, many examples of the application of rendered AI to real-world customer problems. These range from sensor fusion, video applications combining IIR and RGB imagery, to developing synthetic data for urban environments, synthetic aperture radar, an X-ray simulator built on top of rendered by one of our partners, and many other cases. Thank you for your time, and now Katya is going to speak with us about training AI models with NVIDIA Tau Toolkit.
Hello, I am Ekaterina, a data scientist from NVIDIA, and today I'd like to give you an introduction of our Tau Toolkit. Many of you know NVIDIA as a GPU or hardware company, but that's not entirely true. I'd like to cite our CEO here, Jensen Huang, who likes to say that NVIDIA is not a GPU company, it's a platform company. And by saying that, he means that in addition to our hardware products, we also have many software products available. In our software products for AI, we aim at covering the whole life cycle of a deep learning model, starting from data collection and preparation to going through training, and then finally also we have tools for deployment. So in this workshop, the first part is actually addressed by the colleagues from Rendered AI, where they tell you how to create data using their synthetic data generation tools. And in my part, I will tell you how to use our Tau Toolkit in order to train a model using this synthetic data. First of all, let me share with you what assets we have available to enable you with end-to-end AI model training. So first of all, we have a collection of our pre-trained models. These are pre-trained models for different use cases like people detection, vehicle detection, license plate recognition, pose estimation, and face detection. And there are actually many more other use cases available. These pre-trained models have been trained on the data sets curated and collected and curated by NVIDIA, and we store these models on our NGC, the so-called NVIDIA GPU cloud, which is basically a software repository where we have Docker containers optimized for our GPUs. With these pre-trained models, you can bring your own data and you can further adapt these models using the Tau Toolkit. The Tau Toolkit is a zero coding tool for training, and it allows you either to train a model from scratch, adapt an existing one as like the pre-trained models, and furthermore, it allows you also to optimize your model in order to make it the most efficient for deployment. And then finally, after you have put your model through this optimization training step, you have your own model, which you can use for production. This is free even for commercial deployment. And then we also help you with the deployment tools, such as, for example, the DeepStream SDK for video analytics. We also have a set of sample turnkey apps, which I'm not covering in this lecture today. Here I'm showing you how NGC catalog, the NVIDIA GPU Cloud catalog, looks like. So on the main page, we store different collections for different use cases. So we categorize our software in, like, for example, is it a high performance computing software or is it a software for deep learning? So it's really easy to navigate and browse. And depending on what you look for, you can quickly find it also using the search option here. Here I'm showing you how the end-to-end AI development and deployment collection looks like. So you can see here a list of containers which are typically used by deep learning researchers and developers. And you can see here that we have the containers for PyTorch and TensorFlow. These are our versions optimized for our GPUs. We also have software for deployment like TensorRT and Triton Inference Server. We have also speech processing, speech recognition frameworks available. And finally, Tau is also in this collection. So if you want to try it, just go to the NGC, search for this end-to-end development and deployment collection, and find Tau Toolkit there. And I also mentioned that our pre-trained models are also hosted on NGC. So for that, the best way to find it is start from the Tau page, and we have a list of these pre-trained models available. So then if you click to each individual model, you will see such a model card where we basically describe what does this model do, how has it been trained on which data set, which was the distribution of the data set. We also mention what are the limitations of the model and its performance on different hardware. So let me provide you with more details on what Tau actually is. So as you see here, Tau Toolkit supports training for vision and for conversational AI. And underneath, it's basically a collection of Jupyter notebooks, which you can download from NGC, as I mentioned. And there you can just follow step by step the whole process of training, starting from data preparation and augmentation, including, of course, the training step. And furthermore, you can also apply some optimization techniques like pruning and quantization. It all works on the our CUDA-X stack, including NVIDIA Container Runtime, CUDA, and cuDNN. And it's also fully compatible with our TensorRT, the optimizing compiler. Tau Toolkit can run on any of our training platforms, be it any workstation with an NVIDIA GPU, a DJX station, or in the cloud. And the models trained with Tau can be deployed on literally any NVIDIA GPU, also including our embedded Jetson family. Here's an example application I created using Tau Toolkit. So that's me in my home office, and as you see here, it's a gesture recognition application running. So the way I created it, I used the pre-trained model for people detection, and I retrained it with Tau using some open source hand detection dataset. Then using this hand detection model, I cascaded it with a model for gesture recognition, which I just downloaded from the NGC without any further training. And I deployed these two models using DeepStream SDK. And this is all running on a Jetson device, and it has real-time performance. So you see that the models are very efficient. In addition to pre-trained models, we also support a broad variety of state-of-the-art models, including image classification, object detection, and segmentation models. So all these models have been pre-trained on OpenImage dataset, and they are fine to use even for commercial deployment from the legal perspective. I'd like to speak now about optimization techniques. And I know that in the research community, it's often all about accuracy. But when we're dealing with real business cases, it's really very important also to have our models which are performing well, which have high throughput and low latency. And in order to achieve that, we have included some optimization techniques in our Tau toolkit. And the first one is a technique called quantization. Quantization is basically mapping from floating point 32 precision to integer 8. You can also use floating point 16, but as you may guess that integer 8 is more efficient. And converting to floating point 16 is kind of easy, so you basically just round up the number and use it. However, with integer 8, if you just round up the number, you will lose a lot of precision. So in order not to lose precision, you can basically estimate the so-called mapping from FP32 to int8. And there are two ways to do this. The first one is called post-training quantization, or also it's called calibration. For that, you need a separate data set on which you run your model, and you estimate the minimum and maximum values of the weights in the model, and then use it to basically to find this mapping. There's another way to do it by using the so-called quantization-aware training, and basically by doing that, you're learning this mapping during the training. And as you may guess, this is kind of more efficient and precise. And we enable this quantization-aware training in Tau toolkit. So in the exit, you get your model and then the calibration file available together with your model. Another optimization technique is called pruning. Pruning means removing neurons which do not participate in the final prediction. The way you do it is you basically rank these neurons based on their influence in the final score, and then comparing them to some threshold, you just remove those which are not very active. By removing neurons, you also remove the associated connections, which makes the network smaller in size and also leaner and faster in execution. The only downside of this process is that when pruning the model, you may lose a little bit of accuracy. That's why you need a second training round to restore the accuracy after pruning. Automated mixed precision is a technique which is designed to make your training faster. It is also associated with quantization, and it is available in a couple of latest generations of GPU due to the presence of our tensor cores. So the way it works that before the training, so you have your data in floating point 32, but once the data gets through the model, it is converted to floating point 16. When it reached the optimization step, the data gets converted back to floating point 32 to keep the precision on its maximum. And then for the back propagation, it's converted to floating point 16 again. Doing this allows to accelerate AI training. It helps you also to reduce the memory bandwidth, meaning that you can also train larger models or larger batches in faster time. And this feature is also available in Tau. Actually enabling it is really super easy. You just add an extra parameter to the training command. Tau Toolkit also supports multi-GPU training. In fact, it makes multi-GPU training very easy. So the only thing you need to do here is to specify how many GPUs you want to use. In addition, you can also specify which specific GPUs you want to use for this training, and Tau Toolkit will take care of the rest automatically. As I already mentioned, Tau also supports data augmentation, and we include different kinds of augmentation, including blur augmentation, spatial transformations like rotation, zooming in, zooming out, cropping, and padding. And we also have some color transformations. You can easily control it by specifying, for example, the degrees of rotation or the thresholds for color transformations. So you have the full control on augmentation parameters. As I also already mentioned, Tau Toolkit models are fully compatible with NVIDIA TensorRT. TensorRT is our optimizing compiler and the runtime. And underneath it includes a set of optimization techniques like layer and tensor fusion, weight and activation, precision calibration, kernel auto-tuning, dynamic tensor memory, and multi-stream execution. And of course, Tau can be used to train with synthetic data, and this will be the following part of this workshop. The colleagues from Rendered AI will show you how to use Tau to train a model using synthetic data. And last but not least, please let me share with you some NVIDIA resources. So first of all, here's the link to Tau Toolkit, where we have everything from documentation to the link to the quick start guide and instructions. We have our NVIDIA technical blog, where we regularly publish some insights about hardware, software, business aspects. We also have our NVIDIA Deep Learning Institute, where you can learn different aspects of deep learning. Also, the NGC Software Hub link is there, where you can download all this software which I mentioned today for free. And finally, if you want to stay with us, feel free to register for the NVIDIA Developer Program, and the QR code on this slide also leads you to the program registration link. With that, I'd like to wish you happy training, and I hope you enjoy the workshop by Rendered AI.
Hello, my name is Matt Robinson. I am a senior software engineer at Rendered AI, and today I will walk you through training an object detection model using synthetic data. So Chris has introduced Rendered AI at large, and Katya has given an overview of the Tau Toolkit, and I will show how these two can be put together to close the loop on ML. Okay, so the talk is broken up into 5 parts. I will describe the experiment and then show some target samples that we're going to try to recognize Rubik's Cubes in, and then go to the rendered AI dashboard and make sure that the graph is set up to generate data sets that we think will train the model to recognize the objects, and then use a Jupyter notebook that is hosted on NGC to train the model on the data in the web browser, and finally visualize the inferences to see how it worked. So the details of the experiment are as follows. We're going to train an object detection model using an open source notebook, and the one of the steps will be to process the annotations and metadata that come from the synthetic data set into a Kitty label format, and then into TensorFlow record format to be used with the DetectNet v2 model. The backbone object detection model comes from the NGC catalog, where there are several models to choose from, and we'll take a look at those, and then train the model and inference the target images to see how the accuracy looks, to see how well the data set matches. Okay, so here they are. I just went and put Rubik's Cubes in various locations in the house. Some of them are little toy Rubik's Cubes hidden amongst objects. Some of them are sitting in various scenarios with different camera angles. And then on the right-hand side here, you can see a couple of these images actually are synthetic data images as well, just to throw some variety in and see if we can recognize objects in different contexts. And I think the synthetic data graph is built to try to match these as best it can. So let's go and take a look at the graph that we'll use. When you sign up with Rendered AI, there's an opportunity to enter your content code, and with the CVPR 2022 content code, your account will be built off of this workspace. So there's a whole concept of workspaces inside the Rendered AI platform, and you are highly encouraged to go look at the support doc to learn more about all the features that the platform provides. But the point right now is that when you sign up with the CVPR 2022 content code, this particular data workspace is cloned into your account, so it's yours to work with, and already has some pre-built graphs. So this CVPR 2022, sorry, the Rubik's Cube graph here is one that I put together to kind of target, or to make a data set that I thought would train a model to recognize the target images, to recognize the objects in the target images. So the graph ultimately ends in the render node, which generates the images. So the scene is created in the nodes prior, in which the objects are dropped into a container, and the container's on a floor. So you choose various kinds of things you want in the background, and in terms of the placement of the objects that are chosen, the number of objects is a random number between 8 and 15, and the type of object that's chosen comes from one of these 3 branches, and this branch is weighted 4 times heavier than the other ones So effectively, a third of the objects that come in or that are selected are Rubik's cubes, and the other 2/3 are just random objects with different colors to kind of make a bunch of variety, as much as variety as I could kind of squeeze in with this really basic example channel. So if you come over to the datasets library, you'll see that there's already 2 datasets that have been built, and this Rubik's cubes one has 400 images in it. That comes from the graph that we were just looking at, so you can take a look to see, make sure that they kind of look like what you expect. And then we can so this shows also the details of the data sets, and these IDs can be used by the SDK. And let's go take a look at how that works. So now that we're happy with the graph, we think it looks like it's probably going to lead to a data set that trains our model. I've put together this resource on the NGC catalog called Tau with Synthetic Data Fast Demo. So if you sign up with NGC, create an NVIDIA account, then in the NGC catalog online, you can just do a search for synthetic data and find this right at the top. The NGC developers have integrated this deploy with Vertex AI option in the top right, so you can just immediately run the notebook on a Google Cloud Platform in their Vertex AI product. So I'm sparing the details of setting up an NGC account, or sorry, a GCP account. I will just jump over to what you will see once you follow that link. And this is the workbench in Vertex AI view. So this is where you manage the notebooks, and by manage notebooks, it means to change the GPUs that they're going to be deployed on, or any extra disk space that might be needed, kind of your typical cloud choices for managed services. Once you have your notebook here and it's started, then you can open it in Jupyter Lab. And what that means is that you get your Jupyter Lab dashboard with the files that are hosted there on the NGC resource. And one of the steps that takes a few minutes here will be to load the custom kernel that's part of the integration. And so the entire Python environment comes with the package, and we're ready to roll now with all the dependencies in place. So getting into the notebook, we have this kind of intro section that is here for you to read over when you come to run this yourself. The schematic here shows how, what we mean by closed loop ML with synthetic data, where it's all driven by the graph of the rendered AI system. So you configure a graph to create the data set, and then part of our APIs involve an analytics metrics. So we can take a look at the number of objects per image and the size of the bounding boxes, or the color and brightness. So whatever metrics we think are going to be important to the object detection model. And then once those adjustments are taken into consideration, we can go ahead and train and evaluate with Tau and see if the model is in fact has the accuracy we're looking for, or the speed. So and this performance can then additionally inform whether or not we need to update the graph and get the best data set for our purposes. So the first step is to import AnnoTools. That is not built into the kernel and needs to be added afterwards, but I've already been here, so AnnoTools is installed. So that's our SDK from Rendered AI. Once we have all of our dependencies in place, we set up the environment variables for the project, which just kind of says where the data sets are, and the specs file, which is this directory here that has all of our the different configuration files needed for the Tau toolkit. Let's see. So with that in place, we build this thing called the mounts file. So the mounts file is this Tau mounts file that is written to your home directory to help the it's to support the Docker container of Tau, so that the local files are mounted to the right location in the Docker for Tau. This notebook is based, I need to say at the very beginning here, it's based on the Tau DetectNet notebook that is in the NGC catalog. So this is kind of the baseline notebook that NVIDIA built to highlight the strengths of the DetectNet v2 model, and so that's where I got these the mounts details here. So it's nothing too fancy, but it's important to know that there is another notebook out there. Yeah, for DetectNet v2. Let's see. So in terms of the training data, I will log in to Rendered AI with my my alias here. And I used the SDK after the login to get the data sets, and then to kind of create them, or to list them with some structure. So it lists them by name, the description, and then the status. So the description of this bottom one here, CVPR Rubik's Cubes, has 400 images with 400 by 400 resolution. And so now I can look, now the ID is associated with the name in this structure, in this dictionary that I created, and I can just refer now to the data set by name. Just a little hand holding. The point is that we have the data set ID ready to go. And what I'm going to do here is create a directory name based on the data set name, which is CVPR Rubik's Cubes, and then download the data set. So because we're on Google and it's really fast, we already have it here. Oh no, never mind, we're not there yet. So here's the data set metadata. So more details that are provided from the SDK, using the SDK to access the data set. And then downloading complete and unzip it, and then print the contents of the directory. So you see we have the metadata and the images and the masks and everything that comes along for the ride with the data set. So the first step is to convert the annotations to kitty labels. The annotations are general. They're robust and are prepared to support various annotation formats. We have built out conversions for kitty labels, for Cocoa labels, Pascal, and a couple of the SageMaker annotation formats. So now for DetectNet v2, we need to have kitty label formats. So here's just a helper function that'll generate kitty labels. But what's important is to get the mappings files. So the mappings file is out there in the Rendered AI GitHub resource on GitHub. The mappings file, there's a few mappings files there. This one, Rubik Cube, is built to make all objects distractors other than the Rubik's Cube, so that the object detection model only trains on Rubik's Cubes. The default mappings file just treats every toy as its own class, so it's built to detect bubble bottles and Play-Doh tubs and whatever the toys are individually. And there's another example out there for a mappings file that's just called toys, in which all of the objects are just mapped to the toys class. So whatever, just to kind of give some examples of how you would convert a synthetic data annotation to a project-specific annotation format. So we're going to go to Kitty. We're going to use the Rubik's Cube mapping, and then convert. Yeah. So go ahead and do the conversion, and then take a look at them. So here you can see in this particular image, number 97, there was one distractor and one Rubik's Cube, and there's what the kitty label data looks like. So it looks all good. Moving on to now converting the kitty labels into TensorFlow records for use with Tau. Let's see here. This one of the things I do throughout the notebook is to take these specification files, the configuration files for Tau, and I convert them over to a temp. And change the variable names in there. So they're written with like dataset dir as a variable, or I'm treating dataset dir as a variable and then replacing it with the real dataset directory. So so you can see here that now the kitty conversion configuration file now has this kind of elaborate long name of where the dataset is listed. And now that we can verify that the conversion script is accurate, and go ahead and run the dataset convert command from Tau DetectNet v2, and then verify that the TensorFlow records showed up. So all looks good. So step 3, to prepare the model. So we need to go get the backbone from NGC. And this first cell downloads the command line interface for NGC, and then we can call it and take a look at the options. So this lists all of the pre-trained DetectNet v2 models. So there's various versions here. We're interested in this ResNet 18 one, but there's all kinds of DetectNet 2 versions available. So let's see here. So now we're so here we are downloading the ResNet 18, and so now all the weights are here locally for us to use for the notebook to access. And it's time to prepare the training specification. So again, you're going to convert the spec file to a temp file and replace all the dataset dir and project dir to the real ones that we have in this example. And then I went ahead and listed the entire file so we can see all the hyperparameters that are being used for the training campaign. I preserved the resolution of the training images, so they're both 400 by 400. I didn't want to change any of that. The number of epochs is set to 60, and lots of others. But those I think are the only two I changed from the default settings. I didn't want to get too much into the weeds on the hyperparameters. I just wanted to make a training set that would work pretty well. And so I just trusted the NVIDIA engineers to have their default values. So, so now it's time. So now that the configuration file is there and the record and the data set has been converted to TF records, or at least the annotations. The annotations are converted to TF records. The images are there, and so the training can take place. So this takes about 10 minutes. So I went ahead and just did it in another account so we can skip to the future by me just changing tabs. And when the training is done, here at the very end it says that on the validation set, the Rubik Cube class has an average precision of 94.6%. So it looks pretty good. So probably worthwhile now to look a little bit deeper and visualize the inferences. So let's see. So it's the same process as for training. I download the images from a public URL, and then update the inference specification file with the correct directory. And here's the parameters for your inference. We're going to okay, yeah, and then the confidence threshold is set at 90%, and then run the inferences and take a look at the results. So what the point of the exercise is to find out if there's any false positives or false negatives that are jumping out, and then update the graph accordingly. An anecdote here is that when I first set this up, I showed Katya the results, and it was missing cubes that were at an angle. So she immediately recognized that the channel, the synthetic data channel, needed to be updated to not be so directly overhead, and that the camera needed to come down a little bit. And then when I made that adjustment, sure enough, we recognized nearly all of the Rubik's cubes with few false positives. I'm not quite sure why this one up here in the strawberry patch doesn't get found, but otherwise I think it's a pretty good start. Probably more accuracy would come if the images were larger and there was more of them, but I just wanted to get just a small data set to demonstrate the functionality. But if so, that's some hypotheses. I'm not sure if the idea is for a computer vision scientist to look through these and maybe get an evaluation set and a metric to say I would need to update the channel to prevent a particular thing or to capture a particular thing, and then that's what we do at Render, is just iterate with our customers to get these training data up to spec. So thank you, and please reach out with any questions.
Hey, I'm Sam, and I'll be talking about how you develop a synthetic data channel on the Rendered AI platform. So to go over what I'll be speaking about, first we'll recap what the synthetic data channel is. Then we'll talk about the simulation engines and how the rendered AI architecture supports them. We'll talk about digital twin sensors. And next, I'll go over the code base for the example channel, the different nodes that it has, and talk about how it uses the RGB sensor. I'll have a live demo of adding a new Blender model to the example channel. And next, I'll talk about how you deploy a new channel to the rendered AI platform so you can use that almost immediately to generate data sets. And finally, we'll talk about the rendered AI SDK. So to recap what a synthetic data channel is, the synthetic data channel is a container for the simulation engine, sensors, object and background models, and application-specific code to define the physics for the rendering of the synthetic data. So we believe that data generation is a science, and it's a cyclical process. So we believe that it has these 3 steps. First, the synthetic data engineer will build a channel, so they'll develop the nodes. Next, with this channel, the computer vision scientists will use that to build the graphs and generate the data sets. And finally, based off of these data sets, they'll evaluate the results. So they'll look at what's in the data sets, and maybe they'll, realize something is missing because they know what the data requirements are. So what they would do is ask for more data or more different nodes from the synthetic data engineer so that they'll get what they need out of the data sets. So maybe they'll find like a missing background or a missing model, or maybe they want to go in and update the physics. So it's all possible through our platform. So because of this, we believe that synthetic data needs to have a platform and can't be commissioned work. And we provide the tools and documentation so you can build the data yourself. One real world example of this is in the prior experiment that Matt had spoken about. He was not getting the results that he needed from his experiment. So all he did was he went in and modified the camera angle for the data set, and then he generated data sets, and then he found that the new data sets worked a lot better for him. So it is a very quick process, and you could have complete control over it. So now let's talk about the simulation engines and the engines that we support. We support Blender, Omniverse, and DeerSig currently, and there will be more rendering engines to come. So all 3 of these engines are ray tracing and physics-based. Blender is a simple RGB engine that is useful for common camera synthetic images. DeerSig is a render adapted to platform for other parts of the electromagnetic spectrum and useful for atmospheric science. Omniverse is useful for robotics and warehouses. So channels are wrappers around these simulation software packages. So on the right here, you see the diagram of what a channel is, and the question mark, that's kind of where the simulation engine would plug in. Then you'd define your physics and object properties in the custom code that's written in Python, and all of this will get packaged up with Docker, and it'll get containerized and deployed to the platform. And this is what works, and this is what will run in the cloud. So simulation engineers will work with the computer vision scientists and industry experts to get the channels built up. And within these channels, there are simulated hardware platforms that will provide motion and attachment for multiple sensors and sensor types. So maybe a camera or a spectrometer could be mounted to a platform, and it could have motion, or it could also be without motion. So some examples of motion are drone motion, stereo, where you have like a left and a right camera, or walking. And you can change the viewing angles for the cameras. So if you want like an aerial image, you would, have the camera from the top looking down. You could have like a low shot where you want the camera close to the ground looking up. For stereo, if you want like a left and a right camera, you could have 2 cameras defined, maybe a certain distance apart, and you'd essentially get 2 different images. For walking, maybe you'd want like few cameras set up in a certain length with step angle of or step size of like maybe 10 meters. So whatever you need and whatever cameras you need, you can define them within the channels. So a camera is one example of a sensor. It's an RGB sensor, but we support more than that. We have support for black and white. We have a custom synthetic aperture radar or SAR simulator, and we have hyperspectral, multispectral, and infrared support. So on the right here, it's a similar diagram as before. We've chosen Blender here as the simulation engine, and within Blender, here's some examples of the sensor platforms and the way that the camera or sensor mounted to it would behave. So for satellite imagery, that's what's used for SAR. For like the camera, you could have a tripod or have it mounted to a drone. The drone is what's used for DeerSig. And here are two great examples of synthetic data that was generated on our platform. So on the left, we have generated a SAR image of a Star Destroyer from Star Wars. So this is not a real ship. This was never a real ship. It was generated through the model of the Star Destroyer run with our SAR simulator. And on the right is an image generated with DeerSig with a push broom sensor for Earth observation. And this image is of dirt roads and grasslands. So what we found is data sets need annotations, and synthetic data provides the automated creation of pixel perfect data labeling. So we provide every single data set with annotations, so you can use these annotation files and convert them to the different formats that you need and essentially know exactly where any object is within every single image. So now let's talk about the example channel. The example channel uses the Blender simulation engine and a RGB camera sensor to generate data. So it's a very simple channel. There are certain objects that will be dropped from the top into containers, or they can be dropped onto the floor. And it has objects, containers, floor backgrounds, and different modifiers. So the physics for the channel is simply that you're dropping objects, and the render node is the RGB sensor. So let's go over the code base for this channel. So I'm going to jump on over to our GitHub page, and you can jump on over also to follow along. So the interpreter will basically take this code and run it in the container on our cloud, but let's say that you want to do local development. So I'll kind of go through it in a way that you can essentially use this example channel as a template, and you could clone it and create your own channel with this. So at the top level, and reminder again, this code base is github.com/render-ai/example. So at the top level, we have our channel definition file, and the name of this file is, you'll have your channel name first, and it's a .yaml. So if we click on it, we'll go through some of the important pieces in here. So because we're using Blender as a simulation engine, for type, you define it as Blender. We have a few nodes that we are selecting from our Anatools Python SDK that we have available on PyPI. We are reusing the weight and the random ranint, which is the random integer nodes from that package, so we don't have to write it ourselves. And those are kind of the key pieces. So if you're familiar with Python packages, the actual code for the channel is essentially equivalent to what you would see for a Python package. So the code for the channel itself is under packages/example. Setup.py, this is what you've been familiar with before. You can define your versioning and your like authors and like your licensing information in here. So if we go into example, at the high level, package.yaml, this is a very important file. So this is essentially your way of defining how you're taking in the Blender files and like where the objects are located in the blend file. So you could have multiple objects defined in a single file. So for example, let's talk about how there's like 6 or several different containers here, and they're all using the exact same file. So if we open up the containers file itself, all right, so here you can see at the high level, the object names are exactly matching, like with the case and spacing, to your object names here. So light wooden box is here, light wooden box. We have dark wooden box, and so on. So we have some steps that you would have to take to create these Blender files yourself. You'd have to define like your parent hierarchy here. So if you want to know more about how to do that, go to support.render.ai. We have some great development guides there. And I'll also kind of be walking through it a little bit more with a demo of the blend file that I used. Another important piece here is the volume section. So volumes are basically the S3 buckets that we're using to store these individual blend files, and we group them together with like IDs. So this is the ID that we're using for the example channel. Now, if you're going to run this locally, you would basically have a folder created with this exact ID and have all the blend files located there so that you can run the rendering locally. So now let's go back and talk about some of the different nodes that we have. So you can see here that each Python file has a matching YAML file to go along with it. So if we go through the color variation modifier and click through the YAML file, so what this YAML file is it's basically the schema for your graph node. So if you go into the rendered AI UI, let me pull that up here. And if you go into the graph editor, so if you use the CVPR 2022 content code, you can follow along and have these graphs available to you. So I'm going to open up the CVPR Rubik's Cubes graph, and I'm going to open up the color variation modifier node. So here's what the color variation node looks like. And what you can see is you can define some of these like parameters as defaults. So all of these parameters show up in your dropdown. You can define what the different inputs are. So here we have input as like the actual color itself, which is these parameters from the dropdown. And the other inputs is it has to be a type of generator to be an input link. And you can also define what the output link is here. So output is generator. And then you can define how you want it to show up in the list. So we're having it show up in the modifiers list under the color header, and the name of the actual node is called color variation. You would define a YAML file for every single node that you're developing so that you can have control over how it shows up in the UI. And you can even define a like tooltip like helper to kind of give some info on what it is. So for example, if you hover over the eye, you can see that it matches over to the tooltip value on the left. I'll talk a little bit about the dropobjects.py at a high level. If you want to know exactly what the code is and what it does, I would highly suggest for you to just look through it on your own. So there's different ways to go about placement. So maybe you want to randomly drop something like what we're doing, or maybe you want to throw something into the air. Maybe you have certain areas in like a scene or like your background where you'd want objects to generate within. So you want it to be like a bounded. So for example, if you want objects to fill in a parking lot just in like a few different locations, but you want to have like trees on one side, you can define that. We're using the Blender API to do that. And Another example is maybe you want to randomize colors and textures. So we're randomizing colors with color variation, but if you want to get more granular with it, you can go further, can reuse the drop objects physics node that we have, or you could write one yourself. So that's a little bit about the nodes. I kind of want to leave it at a high level because we have a lot of great support talk on our support site that you can read through if you want to dig in more. So now I'm going to go back up to the root level here and talk about the different mapping files that the example channel has and what a mapping file is. So we have 3 different mapping files here. So the files are interfaces with the machine learning engines, and using these files, you can highlight points of interest. So this will help with setting up the annotation files, and with this, you can be as granular or generic as you want with your annotation, and this will essentially label every object as you would like it to. So if we look through the default mapping file, you can see here that there's classes and properties, and for each class, there's a number assigned to it from 0 to 6, and then 99 is a distractor. So basically, distractors are going to get ignored, and here, every single object is assigned to a number, so you want all of these objects essentially to show up in the annotated file. And here, one thing I'll point out is Rubik's Cubes. We have sorted and unsorted Rubik's Cubes. So like, when you mix them up versus when you solve the cube. So that's why we have 2 different types of cubes here, but they're all part of the same class called Rubik's Cube. So this is a little bit different than, for example, if you wanted to just highlight all the Rubik's Cubes in an image. So here you would label Rubik's Cube as 0 and everything else is a distractor. So every other object is set to 99 versus the cube objects that we have are set to 0. So all the other objects are going to get ignored for the data labeling and only the cubes will get labeled. So this is kind of useful for the post-processing step of the data set. So essentially, once you run a job and you have a data set generated, so if you're following along here in the content code, if you click on like the CVPR Rubik's Cubes, you'll see a bunch of options here on the right. So here we ran it 400 times, so there's 400 images in the data set. What you can do is you can create the annotations with the different formats that we have supported here. With these mapping files. So these are the mapping files that we just went over. And Dan will be covering this in a little bit more detail. Next, I wanted to show you how you'd actually go about cloning this repo and adding a Blender object to a channel. All right, so this is going to be a little bit of a live demo. So let's say that you you have a object file that you really want to add to a channel, and what would you do to do this? So for my example, what I did was I went to TurboSquid and I found like a super simple low poly image of like a Mustang. And unfortunately, this is not available on TurboSquid anymore. They seem to have taken it down, but I was able to snag it before they did that. So I had to change a few different things for this blend object. So I have it opened up here. So what I went and did was I resized this because when I first downloaded it, this was a very large scaled car. It was like 40 feet long. And the example channel is real size, like its scaling is like real life. So you'd want to scale everything down to around 2 inches. So when you drop them into a container, everything is kind of going to be the same size and it won't drop like, on top of the container. So next, what you'd want to do is go into the blend object itself and set up the hierarchy. So you rename whatever the top level is here. So I have this name to car. Then you'd want to remove any existing cameras and light sources because we already have a camera defined with that RGB node. So any other cameras would just be extraneous and could mess with the final rendering. And then finally, you'd want to enable rigid body physics. So you could go into here, click on this option here, and toggle it on. And for settings, you'd want to have it enabled and then do disable collisions and then have it set to dynamic. All right, so now what I did was I created my object file and got it ready for use in local development of the channel. And then I went and cloned the channel. And I was working off of the clone. So this is my cloned workspace here on the left. And you can see that this is essentially the same as what I went over. There's a few extra things here. So we have a data directory, which is all the blend files that I went and downloaded for this volume. And this is mapping to that package.yaml file that we spoke about before. We have our graphs directory, which I'll talk about because we'll be using this default graph to run the local development and the local rendering. We have our mappings folder again. We have our packages folder. So what I did here was I went and renamed the existing example.yaml to the name of the channel that I chose. So I chose the name example with toy car. So I renamed it to that. And I also renamed the example package to that name. So it was just like a simple refactor of the name. Next, what I did was I went into objectgenerators.py and I added a new node for the car. So I essentially just copied an existing one. I copied a bubbles node and modified a few other things with how the get blend file generator is getting this name. And then I added the car node to my YAML file for this object generator. So we have a new car node here. And I did the same thing here. I just copied this bubble nodes and then just changed some of the names here. So for outputs, it's going to be outputting a car generator. The tooltip is going to show that it's a car factory. And as for the header, it's going to show up as car. Then finally, I went into the package.yaml and I pointed the car node to point to the file name for car.blend. And I uploaded this car.blend file up into here, into the volume. And finally, now we can kind of play around with the graph. So the default.yaml is the default graph that comes with the example channel. You can use this for local development. So what I went and did was just to run it and test that the car, showed up correctly. I went and removed all the other nodes. I removed all the toys. And I kept the object placement generator and just kept the car in there. So we're going to have basically in graphical format, we would have a car that plugged into the object placement that will, be used, and the object will get dropped into a container, which here we're going to keep the light wooden box that we already have from before. And this container is going to be on the floor that is type granite. And all of these will be running the drop objects physics. And then for render, I changed the size of the image to 512 by 512 just because I wanted it to be really quick. And then the final change I'm going to make is for number of objects, I'm going to change this to just one because, it takes time for the rendering to run. So if you're just doing local development, you want it to be pretty quick. So to run the render, you just type Anna, and it'll start. And what it'll do is create this output directory. This will get auto-generated within it, and you'll have a few different directories here. So annotations is going to be your annotation files that get generated with our rendered AI formatting that you can use to convert to other annotations like we spoke about. Images is going to be the actual image that's generated out of this render. Masks is going to be your image masks. Metadata is any other, like, I guess, metadata that you'd want to know about the image, such as like when it was created or like what are the objects in it. So looks like our image is ready and great. So we have one car in it. Cool. So looks like our new object got added into the channel successfully. So now let's modify this default.yaml a little bit more. Let's bring back all the other stuff. So I'm going to Control Z everything back in because I want to check how all the other objects are going to behave. So we're going to go back to having all the other objects in it. And we're going to have 15 objects again. And I'm going to run Anna again. And while this is running, this will take a little bit longer because now we have 15 objects. I'll kind of show you a few different phases of development that I had here. So for example, I had issues where the car was way too big and it was kind of falling on top of the container because this is all true to scale. Then I got the car a little bit smaller, but it was still too big, and all the other objects would have been like really small next to it. So then I had to play around with the scale a bit more. One example I wanted to show you is sometimes you can have an issue with images that have like an overlap between like the container, and this will happen if you make the image, or sorry, the object model too small in scale. So Blender has issues with objects that are a little too small, I think under 2 inches, because the physics does not behave as expected there. So just something to keep in mind if it's something you run into, try scaling your model up a little bit and that might solve your problem. So we're just waiting for this to finish and looks like it's done. So now let's open up this new image file. Cool. So it looks like all the other objects that we've had existing on our example channel show up here with the new car. Cool. So now what you'd want to do is basically you'd want to deploy this channel to our Rendered AI platform because this channel is now ready to be used to generate data sets in the cloud. So in addition to deploying this, you'd also want to upload this volume to our platform. And for the volume upload, I would suggest to look at the SDK docs to understand how to do that. It's just one command that you have to run. And for the deployment, I have some examples here. For deployment, you basically run the Anna deploy command. You just type that into your command line terminal, and then it'll ask you, do you want to create a new channel or do you want to deploy it to an existing channel? So here I chose that I wanted to deploy it to an existing channel because I'd already created this channel. And then it'll take a few minutes to run. It'll have some output like this where it'll show you like the steps that it's running. And then once it's done, you can go to the workspace on the platform and enable it. So if you go into workspace here, click on the channels, then you'll be able to create a new graph with it. And so if you go into these graphs, I created this graph with this example toy car channel that I just showed you. And what you can see is we now have the car node in the object section here. And I've also added it into the graph itself. So it's going to render with the random placement node. And for data sets, if you want to explore what this looks like after you run the job with it, here's some examples of the images that have come out of this channel. Every single image is different, everything's randomized, and everything also comes annotated. I'll wrap up by talking about our SDK. It's on PyPI and it's called Anna Tools. We use the SDK to deploy channels and manage volumes, but we can do everything that the UI does and more. It's useful for running batch scripts and running jobs and data sets headlessly. SDK.render.ai, we have links for some Jupyter notebooks that we find to be very helpful to learn how to use the SDK, and also the documentation is available at that link. This is what the documentation looks like. We have every function documented just like any other Python package that's out there. you click on this link, you can go and browse our resources repo, which holds a bunch of Jupyter notebooks that help to understand how to use the SDK, but also how you can use the SDK with machine learning pipelines. So some great notebooks I would like to highlight here are generating annotations for data sets, because as I said before, you can run annotations through the UI that run on the cloud, but we have draw type of annotations which can only be run through the SDK. If you'd like to annotate your data sets with 2D or 3D bounding boxes or with segmentation, this is the way that you'd have to do it. Another great notebook is the Dataset Analytics notebook. So you can run analytics jobs to get certain types of information about your data and metrics for statisticians, and this will help you understand if the data that you've generated is useful. And I'll hand it off to Dan now, who will speak more on the post-processing.
Thanks, Sam. So Matt and Sam talked to you about how to generate synthetic data on the rendered AI platform. But I'm going to talk to you a bit about how to extend your synthetic data workflows and to use adaptation and analysis to enhance the performance of your synthetic data once it's generated. So a quick overview of what I'm going to talk about. I'm going to talk a little bit about annotation within synthetic data. Sam talked briefly about that, but I'll touch back to it. I'll also talk about how we can use some different tools to close the reality gap or the domain gap within synthetic data and real data. And then we're going to talk a little bit about quality assessment and how we can use certain tools to better get a sense of the actual quality and comparison of our real data and our synthetic data. And then I'll go into a quick demo about how to apply UMAP to an output data set and compare that data set with the domain adapted data set and how that compares with the real data that you might be training a model to detect. So one of the major benefits of using synthetic data is that annotation is automatic. You don't need to pay a group of people humans to actually go into and label your own data. More so, it's 100% accurate. So you're not going to have to deal with some of the quality issues that come with human labeled data, and that becomes more important when you're working with very complex sensor types and things that maybe are not recognizable to a human labeler. But beyond that, those are kind of the obvious benefits of using synthetic data. But beyond that, it's really configurable and it's extensible such that you can really experiment with the types of annotations that are going to bring the most value to your data. And you can really kind of update those annotations in real time to be able to perform those types of experiments. So Sam talked a little bit about the mapping file and how you can use that to control how the objects that you have in your scene are labeled within your synthetic data sets. And so what Rendered AI provides is a standard data format that includes basically everything you would need to understand your data and label it in the way that you need. So that includes things like 2D and 3D bounding box coordinates, pixel-based mask information. So what exact pixels are represented by each of these different instances and different types and classes of objects. Things like distance from the sensor to get a sense of depth for each of these different objects in your scene, their rotation and things like that, as well as potentially the obstruction level. How much is it obstructed by other objects in your scene? And that's an optional calculation that you can provide in there to inform things like kitty labels. And then once you have all this information, you can, as a post-processing step, generate new annotations for the data that you've already generated in different annotation formats like Cocoa or Pascal or Kitty. And so the ability to take that data and generate multiple different types of annotations from it allows you to really tailor your experiments to include a variety of different information based on these types of annotation that you provide. So when we're looking at synthetic data, we really are mainly concerned with how it compares with the data that you're going to be actually using your model to detect. So, all simulation is really an approximation of reality, or maybe more accurately, sensors are kind of a measurement of reality, and simulation approximates those measurements using digital twins of sensors and scenarios and physics that are involved in capturing that image. So, no matter how robust of a simulation we get, there is still going to be a bit of a domain gap or reality gap between, the simulated data that you have and the actual sensor-based data. There are going to be some unique attributes about your sensor that you may not capture within that estimation, and that's true of any simulation. So what we've found success with is actually using a GAN-based approach paired with this physics-based simulation approach. So training a GAN model to adapt a synthetic data set, the characteristics of that synthetic data set to that of real data. So as you can see here on the left, this is the original synthetic data. And on the right, we've taken that same image and adapted it to the specific data that we are interested in classifying. So the actual objects in that scene have not changed in their location or their composition, but the characteristics of the image as a whole have shifted a bit. And these are the types of things that get picked up when you're training an AI model to detect objects. So the domain adaptation model we use is the CycleGAN approach. So that was developed in 2017. It's kind of the OG domain adaptation model that kind of hit the scene about 5 years ago. And what's great about this approach is that it doesn't require matched pairs for training. So you can take a representative sample of real data and train it to create an adaptation of your synthetic data, even though it's not an exact representation of those same features that are found within the real images. So another big benefit of it is that the translation occurs on edges that are found within the image. And what that provides is a preservation of the overall feature shapes that are involved in your image. And from there, we can say that there's not really a change in the annotation that's required to represent those different objects that are found within the scene. So some of the considerations you want to take into account when you're training a CycleGAN. One is that the from set, the real data that you're feeding in to train that GAN model should be pretty extensive. So we're finding that around 1,000 images provides the best result. You kind of see that in the image over here to the right, where we have an example of 1,300 zebra images, and this shows a pretty robust translation adaptation. But when we get down into kind of the 250 to less than 100 scale, we find a lot of kind of attenuation and different artifacts that are present within the scene. And similarly, you want to make sure that the from and the to set of data sets have those similar objects present that you're interested in. So whether it be, different types of houses or, features of a face, things like that. And those objects should take up a similar amount of the image. So training a domain adaptation model, a cycle GAN on faces where some are, your from set is all very close up images of the face, whereas synthetic data has images of that are faces from a distance. That wouldn't really work as well. So you want to make sure that they take a similar amount of the image. And then what we found is just that training time takes a long time to train. So, and the training time is really more important than the total number of epochs that you train on, because the reason for that is that, the more data you have, maybe the fewer epochs that you would really need to achieve. So we're finding that between 24 and 48 GPU hours is really kind of the sweet spot for getting a model that is effective, but also doesn't overfit to that data that you've got. So the Render AI platform allows for the ability to upload a trained cycle GAN model to the platform. And the format that we use is the PyTorch format found within this link here. And from there, what we can do is we can take that pre-trained GAN and upload it to your rendered organization via our SDK. And then from there, it is really just a web interface or an API call to be able to apply that GAN to your synthetic data sets as needed. And I'll show you a bit of this in the demo later on. So once we have that synthetic data and perhaps we've run a domain adaptation model on it, how do we assess the quality of it, or how do we assess the improvement that the domain adaptation model provided to our synthetic data? And kind of the gold standard or the north arrow that you really want to look for is does it improve my AP scores? But that's just kind of a single metric there, and it doesn't necessarily highlight where the data has improved, what sorts of features have been included into the synthetic data, where it can be improved, what's maybe missing from that data. So what we found is that viewing these data sets in embedding feature space allows us to really look at what features are found within each of these images, what sorts of things is an actual AI model picking up on, and then we can highlight the differences between clusters of features found in real images versus the clusters of features found in synthetic data. And if they don't quite overlap, then maybe there's some more work that we need to do in capturing those specific features. So how we use this is we implement a UMAP design, and UMAP stands for Uniform Manifold Approximation and Projection, and it's really a way to intelligently reduce the dimensions of our data. So if we apply a CNN, a convolutional neural network that includes a feature pyramid network, we can use the patterns found within those reduced dimension spaces and then reduce them further to 2 or 3 dimensions, such that we can actually visualize those what are really images in a 2D or 3D space. So that's sort of the concept behind it. What we have here is kind of what that looks like in 3-dimensional space. So I'm going to open up the platform and show you a bit of how to do this and what this really allows us to do with the data. All right, so here I am within the Rendered AI platform. And so I have generated some data using what I'm interested in this case is looking for cranes within satellite imagery. So I've generated some synthetic data with these tower crane objects within various RGB satellite imagery. So you can see that this is an example of some cranes. They've been simulated to match the 2D backgrounds that they've been placed into these 3D assets, placed within these backgrounds that include things like time of day and location, so we can estimate the sun shadows, and the simulation is able to match the type of distortion that is included within each of these backgrounds. But how does it really match up with the data that I want to use this model on? So in this case, we want to use it on XView data. So XView is it's an open data set of satellite imagery that is pretty widely used within the satellite imagery space. And what I've done is I've actually uploaded an existing set of real data to the platform. So not only can you generate data within the platform, you can also upload existing real data sets and then use those for analyses. So I've also applied a domain adaptation model here. So if we see here, we can go to this GAN datasets tab here, and we can go and provide an existing pre-trained GAN that I've uploaded to my organization here. So I've done that already, and I've produced this GAN adapted model, the same data, but it's been adapted using that process. So now I want to understand how this GAN adaptation, how it's affected the output data set, and whether that has improved the feature richness of my data. And with that, what I can do is select these 3 data sets and click compare. And that will bring us to our UMAP analysis pane here. So we can click on the XView data to use that as the fit data set. And then we can go ahead and click compare. So I've done that already over here in this tab. So here you can see the 3-dimensional plot output of the UMAP analysis. So what we can see here is that the blue dots represent our XView real data that we're looking to classify. The green dots represent our synthetic data that we've generated. And then the orange dots, rather, are those synthetic data images that we've applied the GAN model to. So you can see just right off the bat that the green dots are very heavily clustered in this bottom right area, whereas the domain adapted dots, the images here, cover a much wider portion of the real data set, of the embedding space of the real data set. So we can dig a bit deeper in there, so we can see, okay, the images in these clusters, they're pretty bright. That's a domain adaptation, a domain adapted image. You can kind of see it's a bit more reddish, a bit darker, and that is kind of the output, the matched output of the real data that's adapted that domain to. So you can see a bit darker, a bit redder, and that is in line with some of these other images that are kind of a bit darker, a bit hazier maybe. So some of the characteristics may be sensor based, and this is sort of the way to bridge that gap. We can also see over here that there's some images that are not within cluster at all within the real data set. And you can see in a lot of these images, they're pretty dark. So we may not really be able to pull too many features out of that to begin with. but that, or we may not really be generating data that is similar to this in this sort of way, these dark regions. And you can also see maybe there's some areas of water that maybe we haven't captured here. So that is to say that if we look at the features that are out of cluster, you can really see trends in what sorts of features exist within the synthetic data and what sort of features do not. We can also change the feature size. So if you remember, we're using a feature pyramid network and reducing those dimensions using UMAP. So we can choose different levels of that feature pyramid, and that changes the output of our 3D plot here. And you can kind of see it follows a similar trend, but maybe other certain images will be outside of cluster in various feature pyramid levels that weren't before. So you can kind of pick out what's being captured and what is not. You can do that all the way down to 64 by 64. So that's kind of a taste of what we can do with domain adaptation, what the effect of that is on our data, and then how we can use tools like UMAP to go in and then analyze that data, find the features that exist within our synthetic data and those that do not, and better get a sense for how we can improve the synthetic data that we're generating to better match what we're looking to classify. And with that, I'll hand it back to Chris to conclude.
All right, so thank you very much from the Rendered AI and the NVIDIA team for taking some time out of your day to spend a few minutes and listening to us talk about synthetic data and the things you can do with Rendered AI and NVIDIA. And then, of course, we hope that you were able to follow along a bit and that you've been able to sign in and try out Rendered. If you have any questions, please feel free to follow up with any one of us. I've listed out our emails here, and we absolutely look forward to seeing you. And if you were in person at CVPR, we hope that you enjoyed the show. And then if not, then we still hope that you were able to enjoy some technology that week as well. So take care and let us know if you have any questions.